All right. Good afternoon, everyone, and welcome to MOS Live. My name is Becca. My pronouns are she and her. And today I will be your moderator for the Virtual Planetarium Exploring Space program. Now, during this presentation, if you are joining us on Zoom and would like to ask any questions or answer any of our educators' questions, you can type them into the Q&A box. If you're joining us on Facebook and YouTube, we're super excited to have you joining us, but please note that we are unable to see any of your questions or comments during the live broadcast, but we do hope that you enjoy following along. If you would like closed captions and are joining us here on Zoom, you can go ahead and click on the closed caption button and select show subtitles. So with that, I think we are just about ready to get started, and why don't we go ahead and meet our educator for today.
Thanks, Becca. Hi, everybody. My name is Katie. My pronouns are she and her. And today I'm going to be your educator and your pilot as we explore space. So this month we have been talking about the weird, wacky, chaotic pasts of our solar system and various objects within it. So as our final episode of this month's theme, we are going to be talking about a few collisions that have happened in our solar system that have either led to the formation of a moon or the destruction of a moon. And if we get through that material, we'll talk about some other collisions in our solar system as well, because cosmic collisions are one of my favorite things to talk about in space. Who doesn't love a massive, violent space explosion? All right, so to get us started, I'm just going to move us on over to a program called Worldwide Telescope. This is a free open source program that you can download at worldwidetelescope.org/download. There is also a web version if you're interested in using that instead, if you don't want to download anything. But it simulates our solar system. Right now, we're looking at the orbits of the planets plus Pluto because we wouldn't want to leave it out, although it is not a planet, but its orbit is here. So right at the center there, we have the sun right in that crosshair, and then Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, which is that blue orbit line. So our two destinations, one of them is very close by. It's actually our own moon, and we are going to explore how our moon actually formed a very, very long time ago. So we can just fly there and get a nice up close view of our nearest neighbor. So the moon is about 250,000 miles away from the Earth, and I'll zoom us in. So, you know, it's not exactly, it depends on kind of how you're measuring this distance, but it's not super, super close, right? It took astronauts 3 days to actually get to the moon for the Apollo missions. But compared to other objects in space, it's very close by. If we look at its surface, or the side that we can see from the surface of the Earth, we can see lots of darker areas, lots of craters on its surface. The moon is tidally locked with our planet. So that means we always see the same side of the moon. The same side is always facing the Earth. And that is because the time it takes the moon to orbit around the Earth is the same amount of time that it takes for it to spin once. So we will never actually see the opposite side unless, of course, we send spacecraft or astronauts, right, to explore the other side of the moon. So we do have pictures and things like that. But how did it form? Why is it there? How did it get all of these cool markings on its surface? And for that, we have to look back about 4.5 billion years into the past. And that's about when the solar system formed, about 4.5 billion years ago, 4.5 to 4.6 billion years ago, if you want to be super specific. And around that time, the solar system was a very chaotic place. Objects that had clumped together or coalesced to form planets were still very, very hot, just basically made of molten rock. And it's thought that there was a moon, or an object, essentially the size of about Mars, that collided with the Earth a very, very long time ago. So let me switch and show you an artist's illustration of what this may have looked like. So this object has been called Theia. And again, it was about the size of Mars, and it actually hit the Earth at, astronomers believe, about a 45-degree angle, causing a massive, massive explosion and just sending so much debris out into space that got stuck in orbit around this. I like to call it the proto-Earth because it wasn't quite Earth as we know it now, but it got caught in orbit around this proto-Earth and eventually kind of clumped together to form our current moon. Now, this is not the only formation theory that is out there. There are other ones as well. But the giant impact hypothesis is the most commonly accepted hypothesis of them all at this time. And that's because of the evidence that astronomers currently have for this particular hypothesis. So things like looking at the Earth's spin compared to the moon's orbit. If we go back into Worldwide Telescope, and we're going to make everything really huge, unrealistically huge, and we can look at the orbits of the moon compared to the Earth, it's about 5 degrees tilted outside of the plane that would line up with Earth's equator. So it's actually very, very close to lying on the same plane. And that is actually a significant piece of evidence that there would have been some kind of impact that sent lots and lots of material from both objects out into space, and then eventually kind of causing this entire system to settle down almost as if it's one system. So that's one piece of evidence. The Earth-Moon system in general has a very high amount of angular momentum, or almost like amount of motion, compared to the other terrestrial planets or the rocky planets in our solar system. There have been moon samples that have shown that the moon had been molten down to a very substantial depth. The exact depth measurement is not known, but moon samples have suggested that it was molten for a very long time and also at a very deep level. So that is also pretty indicative of a massive impact, like in this particular hypothesis. The moon also has a very small iron core, similar to the Earth. Collisions in general are a pretty big part of our solar system's early days from the solar system formation, and it's in general just consistent with what we've seen evidence for in other planets and other theories like planet migration and things like that. And also the Earth and the moon are made up of a lot of the same stuff. They share a lot of common materials, which is certainly something that would suggest that a massive impact kind of just shuffled all this material together. Some of it was recaptured by the Earth and some of it clumped into the moon. So it makes sense that they would share some materials, but it also makes sense that they wouldn't share a certain type of material called volatile materials, essentially. So these volatile elements, these volatile compounds, are easily vaporized. So something much larger like the Earth could keep a lot of these compounds in a massive impact, whereas something very small like the moon would probably lose a lot of them because it doesn't have an atmosphere, doesn't have a ton of gravity to hang on to these easily dissolvable compounds. So we do see differences there as well in these volatile compounds, which is also evidence to support the giant impact hypothesis. So I'm going to pause there and see if any questions have come in so far.
So we have had a question. Perhaps we could talk a little bit about how the sun might also affect the moon's orbit, if at all, or is it really just the Earth?
Yeah, that's a really good question. So because the moon is in orbit around the Earth is the kind of primary object that is kind of controlling the moon's orbit, but the moon is technically also orbiting the sun because the Earth is orbiting the sun. So they are both going around the sun together. And, you know, at various points in the history of our solar system, some objects had been orbiting the sun that eventually became moons and started orbiting different planets in our solar system because they got a little bit too close. So because the moon is so much closer to the Earth than it is to the sun, the Earth is really the main gravitational pull that we see kind of dictating the moon's orbit. But both are still orbiting the sun because the sun is the most massive object in the solar system and also has the most gravity because of that. So I hope that makes a little bit of sense.
Definitely. And we did have another question that just came in, kind of getting into what I know you're about to talk about soon, which was what did Saturn look like then?
Ooh, that is a very good question. And I am going to talk about that in just a few minutes. So I'm going to hold off on that question for now. But I love it. I love the way you're thinking. Are there any other questions?
There's one more that I feel like we could get to now before we move on. And this is a very good question, sort of wondering about what would have happened to all of the debris, since there probably was a lot of debris after a collision like that. So what is the theory about where that all ended up?
Absolutely. So that debris is what astronomers believe went into actually creating the moon, into forming the moon. But there's probably some material that maybe didn't actually end up coalescing into the new Earth or the moon, and that maybe got flung out into another part of the solar system. But for the most part, it went into making the moon. The Earth may have also had a little ring around it for a while before the moon actually completely clumped together. So most of that debris is in the moon or in the Earth.
Awesome. Thanks, Katie.
Yeah. So before we move on to talking about Saturn and the history of Saturn and its ring system, I did want to show a video of the moon over time. So what happened after it formed? Because the moon went through many stages over 4.5 billion years that brought us, or that brought it to the way that it looks when we look up at it today. So this is a video that was put together by NASA with some data from the Lunar Reconnaissance Orbiter. So we've got this animation of the moon just after formation, just after coalescing, eventually cooling off. And again, the early solar system was a very chaotic time. So it wasn't nice and neat like it is today. So objects collided a lot more than they do now. So you can see that massive collision was actually an asteroid or a very large impactor that hit the southern pole of the moon, creating its largest, oldest, and deepest impact crater on its surface. It's called the Aitken Basin. After this, it was followed by a period of bombardment by just a ton of solar system objects, a lot of asteroids, things like that. It's said that if you tuned in last week, we talked about planetary migration. And so this whole planetary migration theory potentially made asteroids fly around in the inner solar system, which is where we see a lot of this kind of bombardment period going on a few billion years ago that eventually drove volcanism on the moon. And so all of these dark patches that we see on the moon, they're called maria, which means seas, because a long time ago, folks thought that they were actual liquid seas on the surface. So they're called maria. But now we know that they're basins of basalt. So just leftover materials from volcanoes. And of course, the moon gets bombarded quite a bit throughout a few billion years, just because it doesn't have an atmosphere, doesn't have a magnetic field, doesn't have much to protect its surface. So you find a lot more craters on its surface than you would on the Earth. And then you'll notice that a lot of the craters on the moon are actually, you can see like these little streaks coming out of them. And that's just a result from an impact that is kind of lifting up layers from the surface of the moon. So we see a whole bunch of these particular, they're called ray craters, with all of those kind of streaks moving away. So that is how we have our current moon and the way it looks today. All right. So let's go ahead and head out into the outer solar system. We're going to visit Saturn now and talk about its rings. So I'll set course for Saturn. And I think I can probably just leave it real nice and big. Again, I've bumped up the sizes of the planets. So if you see one kind of photobombing in the background, like you can see the sun and Jupiter right there that look really, really big. That is not the case, but it definitely helps us see them. So Saturn's rings are mesmerizing, right? They're honestly my favorite part about Saturn, but it did not always look this way. Saturn used to be just the planet without any rings, and it didn't have rings until fairly recently. So I mentioned that the solar system is about 4.5 billion years old. Saturn's rings are only about 100 million years old, which is, it sounds like a really long time, but it's actually not that long at all when you compare it to the age of the solar system. Even if you were to look at the Earth, 100 million years ago, dinosaurs were roaming on the surface of the Earth. So if they were able to use their tiny hands to look through a telescope, they wouldn't have seen any rings around Saturn at all. So what actually caused the rings to form? Well, it is another moon. So a moon that was very incredibly icy, because Saturn's rings are made of water ice, bits and pieces of it. So they're not actually solid. They're like, chunks of it, either super teeny tiny grains of dusty ice up to the size of like a yacht. There are trillions of these pieces. And they probably came from a moon, an icy moon, that got a little bit too close to Saturn. It got within what's called a Roche limit. A Roche limit is the radius around an object where if another object crosses it, it will be torn apart by tidal forces. So basically the gravity on one side of an object, because it's closer to Saturn, for example, is going to experience a stronger gravitational pull than the other side of that object. And so it ends up getting torn apart completely. And eventually all of those particles that made up that moon, that very icy moon, settled into the ring system that we see today. So there's another animation that I have of this particular instance, and it is by Nova, and I just clipped the video, so it's actually part of a longer video, but here it is. Let's see, here we go. So this is kind of just an animation of the surface of what an icy moon like that might look like, and what ends up happening as the tidal forces start to take over. So this moon has crossed, again, that Roche limit, and Saturn's immense gravity is tearing it apart into trillions and trillions of pieces of ice. Right, so we see more of it disintegrating. This is maybe what it would look like up close. These are really beautiful animations, some of my favorite ones that I found. And eventually, it probably didn't take very long either. They settled into the kind of plane that they're all orbiting around Saturn in today. And you'll notice that Saturn's rings are very, very thin. From this angle, it's kind of hard to tell because you're just right up in the individual chunks of ice in Saturn's rings. But the rings themselves are actually very, very, very thin. So if we look at them from the side, they basically disappear. In some places, they get as thin as 30 feet. But if you compare that to how wide it is, or how far across it goes, which is about 3/4 of the way from the Earth to the moon. So it's about 175,000 miles across. You compare that to 30 feet. in some places, the rings end up being much, much, much thinner than a sheet of paper by many orders of magnitude. All right, you might also have noticed there are some gaps in the rings because the rings do evolve over time. They're not just going to stay like this. So 100 million years ago, the moon got torn apart and it formed the rings. But over time, astronomers have seen data suggesting that Saturn is also losing its ring system. So there are a couple of NASA spacecraft in particular that showed evidence to support this. So first off was the Cassini mission, which orbited around Saturn from 2004 to 2017, way longer than intended. Cassini was one of the best spacecraft ever. It gave us so much data, so many cool discoveries. We learned so much about some of Saturn's icy moons that are outside of the Roche limit, that are not going to disintegrate and become more of Saturn's rings, but instead have these massive liquid water oceans underneath the surface, and other moons that have liquid, like oceans on the surface, just not liquid water. They're actually liquid methane, and on Titan, things like that. So Cassini is one of my favorite missions, but getting off course here. But Cassini measured that a lot of the particles in the ring system here are being charged by the sun. So the sun emits a lot of radiation. These are called cosmic rays, and they end up charging the ice that is in the rings. And so once those particles become charged, they get stuck in Saturn's magnetic field. The magnetic field lines end up actually pulling these particles into the Saturnian atmosphere. And as soon as they hit it, they disintegrate, essentially, just like the Cassini spacecraft, when it was done with its mission, dove right into the atmosphere of Saturn, started to experience a whole lot of friction, and eventually just vaporized in the atmosphere. And so that's happening to Saturn at a fairly quick pace. Astronomers believe that in 100 to 300 million years more, so from now to another 100 million years or so, it will probably not have rings anymore. And the Voyager 1 mission, which was launched back in the 1970s and flew by Saturn and the other gas planets as well, also took some of these measurements of the particles in Saturn's ring system. And so the data from Cassini was able to be compared to this Voyager data. And that's how astronomers are fairly confident that Saturn is losing its rings very quickly, and also that they are much, much younger than initially thought by astronomers. All right, and again, that's a whole lot of information. So if any other questions have come in, I would be happy to take them.
We do have several questions, and I think we'll maybe start with a few on Saturn before moving to our moon. Someone was wondering, why did the ice moon suddenly fall within the Roche limit and get torn apart 100 million years ago? Did something perturb its orbit?
That's a really good question, and I'm not sure. It is very possible that this moon had been in a stable orbit, and maybe there was another moon of Saturn's that kind of got in its way and maybe sent it off on a different course. Its gravity maybe influenced it a little bit, or maybe there was an asteroid kind of floating by that got caught in Saturn's gravity, started orbiting around it. Maybe that were to perturb the moon that got within that limit of Saturn, or maybe the moon wasn't really orbiting Saturn at all and it was just kind of floating by. There are different possibilities, but I don't know for sure. That's a really good question.
Awesome. And what gives the rings their coloration on Saturn?
Yes, another good one. So the rings around Saturn, since they're made of ice, they're highly reflective. So that's why they appear so bright. A lot of them have this kind of whitish color. The darker ones are just less, they're kind of wispier. You can kind of think of it like less dense. There's more gaps in between them. So they just look darker overall because not as much sunlight is being reflected off of them. This gap here, this really massive one, is called the Cassini division. And that is a complete gap in the ring. So this isn't actually a ring itself, but it's caused by a moon whose gravity combined with Saturn's gravity is influencing those particles and they're kind of separating them.
Awesome. And Noah H5 is wondering, how did the ice moon form that had formed Saturn's rings?
Yeah, so that's kind of hard to say, but it probably formed very similarly to all the other objects in our solar system, which was just a whole bunch of gas and dust that clumped together, that was spinning, and clumped together to form that particular object, that moon. In an early solar system, after a star formed, there's a lot of extra debris that's orbiting around the star. And so that's the debris that planets and moons and asteroids actually come from, because that material clumps together. And so then once you have all of that material clumped and then a lot of the rest, the remaining debris kind of gets blown away by the sun. This again is in the early solar system. You're just left with a whole bunch of solar system objects. So I am assuming that a whole bunch of ice from this kind of period of the solar system clumped together and formed that icy moon that eventually got stuck around Saturn and crossed that line, that Roche limit.
Very cool. And I know we are just about out of time, so I want to take one more question, maybe switch to the Earth and our moon for this one. This is a really great question. I remember this was something that I was asked a lot when I love talking about this thing too. Should there be remnants of the body that originally collided with the Earth? So Theia, should we see that somewhere?
Yeah, that is a very good question. So if we're talking about like an impact crater, if that's the type of evidence that you're talking about, that's going to be really tough because this impact was so powerful and so large that it basically changed our planet completely. This impact generated so much heat that our entire planet was just molten rock at the time. That's why I don't really call it the Earth. It was more of this proto-Earth because it was in no way like the Earth that we see today. So basically, it kind of completely changed after that. And it's because it was molten rock and we have all of these volcanoes and geological processes over time, that erases a lot of the Earth's past. So that's kind of evidence in terms of impact craters and things that you could go search for. But also there are some components that the Earth probably has because of this collision. Same thing with the moon. So we see a lot of the same materials in the Earth as we do in the moon. And I imagine that those materials, a lot of them are from that object, Theia.
Yeah, that's so interesting to think about, thinking about those minerals that may have come from Theia that are now incorporated into our regular rocks just by recycling. Thank you so much, Katie. I'm so sorry we're out of time and we didn't get to all of the questions, but I do want to give you the opportunity to say your goodbyes.
Yes, thank you all so much. I hope you had fun and I'll see you next week.
Awesome. Thanks, Katie. And I hope you all enjoyed today. If you did enjoy this, we have more of these coming up. So definitely check out mos.org/MOS at home for any additional information about our live streams, or if you want to check out next week's. We were exploring with Worldwide Telescope today, but another really good resource to use is NASA's EYES if you want to go check out some of the planets around here. So you can go to eyes.nasa.gov. And if you enjoyed this and are willing and able to support the museum, you can head to engage.mos.org/welcome. So thank you all so much for coming, and we will see you all next time.